Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will see that how to solve the problems based on the line regulation and the load regulation. So in the previous video, we understood that what is line regulation. So we have seen that this line regulation is the ability of the power supply or the voltage regulator to maintain the constant output voltage despite the change in the input voltage. So this line regulation can be defined as this delta V out divided by delta V in, that is the change in the output voltage due to the change in the supply voltage or the line voltage. And the unit of this line regulation is millivolt per volt. And in the percentage, it is defined as this delta V out divided by delta V in times 100. Similarly, we also understood about the load regulation. And we have seen that this load regulation shows the ability of the power supply or the voltage regulator to maintain the constant output voltage despite the change in the load current. So this load regulation is defined as this no load voltage minus full load voltage divided by full load voltage. And for the percentage, it is multiplied by the 100. So now let us take some examples based on the line regulation and the load regulation. And here, during our examples, we will take the Zener diode as the voltage regulator. So in the earlier videos also, we have solved the many examples based on the Zener diode. And during those examples, we have replaced the Zener diode by its Zener voltage. So far, we have assumed that the Zener current of the Zener diode is 0. But actually if you see, then the Zener diode will also have some Zener resistance. Because if you see the characteristic of the Zener diode, then this is how it will look like. So in the reverse bias, up to the Zener voltage, there is a no current flowing through the Zener diode. And once the reverse voltage crosses the Zener voltage, and as soon as it goes above the Zener knee current or this IZK, then the Zener diode starts conducting. And then after, for the ideal Zener diode, the voltage across the Zener diode should remain constant. But actually if you see, then with the increase in the Zener current, the Zener voltage also slightly increases. So this increase in the voltage defines the series resistance along with the Zener voltage. So this resistance is known as the Zener resistance and it is defined as the RZ. That means beyond this IZK, when the current starts flowing through the Zener diode, then with the increase in the Zener current, the voltage of the Zener diode will also slightly increase. And the voltage at this IZK is defined as the Vz0. So many times in the question, the Zener knee current is given as the 0. So in that case, this Vz0 is defined as the 0 current Zener voltage. But in general, this Vz0 is the voltage of the Zener diode at the IZK. So with this Zener resistance, if we see any circuit of the Zener diode as a voltage regulator, then equivalently, this Zener diode can be replaced by this Vz0 in series with this RZ. So due to the series resistance of the Zener diode, when the source voltage changes, then due to that, the Zener current will also change. And hence, the voltage across the Zener diode will also change. Similarly, with the fixed value of the source voltage, if the load current changes, then due to that, the current through the Zener diode will also change. And hence, due to that, the voltage across the Zener diode will also change. So we can say that due to the series resistance of the Zener diode, when the source voltage changes or when the load current changes, then due to that, the output of the Zener diode will also change. And due to that, the output across the Zener diode will not remain constant. So due to that, when we use the Zener diode as the voltage regulator, then we will get the finite value of the load regulation and the line regulation. So considering the series resistance of the Zener diode, let us see the few examples based on the line regulation and the load regulation. So here in the first example, the 6.8 volt Zener diode is used in the circuit. So here for the Zener diode we have been given that its voltage Vz is equal to 6.8 volt when the current that is flowing through the Zener diode is equal to 5 milliampere. And here we have been also given the series resistance of the Zener diode. So here we have been given that the nominal supply voltage for the given circuit is equal to 10 volt. But due to the fluctuations, it can vary between the plus minus 1 volt. So here, for the given circuit, we have been asked to find the line voltage in millivolt per volt. And similarly, we have been also asked to find the load regulation in the millivolt per milliampere when the load current is equal to 1 milliampere. So let us find that. So here, first of all, we have been given that the Zener voltage Vz is equal to 6.8 volt when the current through the Zener diode is equal to 5 milliampere. And here, the value of the Rz is equal to 20 ohm. So it means that this voltage across the Zener diode is equal to 6.8 volt when the current through the Zener diode is equal to 5 milliampere. So here we can say that this voltage Vz is equal to Vz naught, that is this voltage plus Iz times Rz. So here this Vz is equal to 6.8 volt when the Iz is equal to 5 milliampere. So we can say that this Vz naught plus 5 milliampere times 20 ohm is equal to 6.8 volt. And here this 5 milliampere times 20 is equal to 0.1 volt. So from this we can say that this Vz naught is equal to 6.8 volt minus 0.1 volt. That means the value of the Vz naught is equal to 6.7 volt. So with the Vz naught, if we see the equivalent circuit, then this is how it will look like. So for the given circuit, now let us find the value of the line regulation and the load regulation. And first of all, let us find the load regulation. So here, to find the load regulation, first let us find the no load voltage. That means at that time, the current through the load is equal to 0 milliampere. And here, we will find this load regulation at the nominal voltage. So in this condition, let's say this no load voltage is equal to V01. And this V01 can be given as this Vz0 plus Iz times Rz. So here we already know the value of the Vz0 as well as the Rz. So the only thing that we need to find is the Iz. So here this Iz can be given as this 10 volt minus 6.7 volt divided by this 20 ohm plus 0.5 kilo ohm, that is equal to 500 ohm. So that is equal to 3.3 volt divided by 520 ohm, and that is equal to 6.346 milliampere. So now let us put the value of the Iz in the above expression. So we can say that this VO1 is equal to 6.7 volt plus 20 ohm times 6.346 milliampere, and that is equal to 6.826 volt. So in this way, we found the value of the VO1. So similarly, let us find the output voltage when the current through the load resistor is equal to 1 milliampere. So whenever this load current is flowing through the load resistor, at that time, this Zener current Iz can be given as this Is minus IL, where this current is the Is, while this current is the load current, and the remaining current will be the Zener current. So here, the value of the load current is equal to 1 milliampere. So here, to find the Zener current, first we need to find the value of the Is. So that can be given as this 10 volt minus Vz, that is this entire voltage, divided by 500 ohm, and that minus 1 milliampere. So here the value of the Vz is equal to 6.7 volt plus 20 times Iz, that is the drop across this 20 ohm resistor. So this entire term corresponds to Zener voltage, and that will get divided by the 500. That means we will have this Iz is equal to this term minus 1 milliampere. So if we further simplify it, then we can write it as this 500 times Iz, that is equal to 10 minus 6.7 minus 20 times Iz minus 0.5 volt. Because when this 500 ohm gets multiplied by the 1 milliampere, then we will get the 0.5 volt. So if we further simplify it, then we will have this 520 times Iz, that is equal to 2.8 volt. Or we can say that this Iz is equal to 2.8 volt divided by 520 ohm, and that is equal to 5.384 milliampere. So from this we can say that this output voltage VO2 is equal to 6.7 volt plus Iz, that is 5.384 times 20, and that is equal to 6.807 volt. So in this way we got the value of the VO1 and the VO2. So we know that this load regulation can be given as this delta V out divided by delta I naught. So here the change in the output voltage is equal to 6.826 volt minus 6.807 volt, and here the change in the output current is equal to 1 milliampere. So we can say that this load regulation is approximately equal to 19 millivolt per milliampere. So from this we can say that for the given circuit, the load regulation is equal to 19 millivolt per milliampere. So similarly, let us find the line regulation. So here, the line regulation can be given as the change in the output voltage to the change in the input voltage. So here, the supply voltage or the input voltage is changing by the plus minus 1 volt. So due to that, let us find the change in the output voltage. So here, we will find this line regulation at the no load. So in the no load condition, in general, here the output voltage Vout can be given as this Vz0, that is this voltage, plus Iz times Rz. And here this Iz is equal to this Vs minus Vz0 divided by this Rz plus R, where this R is equal to 0.5 kilo ohm. So in general we can say that this output voltage is equal to Vz0 plus Iz times Rz. So here, now if the supply voltage Vs changes by the delta Vs, then due to that, let's say the output voltage is changing by the delta V0. So here, this Vout plus delta Vout can be given as Vz0 plus Vs plus delta Vs, that is the change in the supply voltage, minus Vz0, that is this voltage, divided by R plus Rz times Rz. So let's say this is the equation number 1 and this is the equation number 2. So here, due to the change in the supply voltage, if we just want to find the delta change in the output voltage or this delta V0, then we can find that by subtracting these two equations. So if we subtract the equation number 1 from the 2, then we will get the delta V0. So in that case, this will get cancelled out, and similarly, this Vs will also get cancelled out. And effectively, we will have this delta Vs times this Rz divided by R plus Rz. Or we can say that this delta Vout is equal to delta Vs times this 20 ohm divided by 520 ohm. So here we have been given that this delta Vs or the supply voltage is changing by plus minus 1 volt. That means due to that, here the change in the output voltage is equal to plus minus 1 times this 20 divided by 520, and that is equal to plus minus 38.46 millivolt. That means whenever the supply voltage changes by plus minus 1 volt, then the output voltage will change by plus minus 38.46 millivolt. Or we can say that the line regulation is equal to plus minus 38.46 millivolt per volt. So in this way, for the given circuit, we also got the value of the line regulation. So now, let us move to the next example. So in this question, we have been given the Zener Diode based voltage regulator, and it is used to power the car radio at the 9 volt. So here, this voltage regulator is powered using the automobile battery, and we have been given that the voltage of this battery may vary from 13.6 volt to 11 volt. And here, the current through the radio is varying from 0 milliampere to the 100 milliampere. That means whenever the radio is in the off condition, then it is drawing the 0 milliampere. And whenever it is operated at the full volume, then it is drawing the 100 milliampere. That means here, the full load is equal to 100 milliampere, while the no load condition is equal to 0 milliampere. So here, for the given circuit, we've been asked to find the line regulation as well as the load regulation in the percentage when the source voltage is equal to 13.6 volt. And here, we've been also given the value of the Zener resistance, that is equal to 2 ohm. So let us find that. So here in the circuit, we've been given the value of the Vz0. So with considering the Zener resistance, this is how the equivalent circuit will look like. So here, first of all, let us find the value of the load regulation. So as you know, the load regulation is given as the no load voltage minus full load voltage divided by full load voltage. So to find that, first of all, let us find the no load voltage. That means whenever the current that is drawn by the radio is equal to 0 milliampere, or effectively when it is not connected in the circuit. So here we will consider the value of the battery as the 13.6 volt. So at this battery voltage, this output voltage across the Zener diode can be given as this 9 volt plus Iz times 2 ohm. So here, first of all, let us find the value of the Iz. So here, this Iz is equal to 13.6 volt minus 9 volt divided by this 18 ohm plus 2 ohm, that is this current. And if we calculate the value, then it will come out as 0.23 ampere. So from this we can say that here the no load voltage is equal to 9 volt plus 2 times 0.23 ampere, that is equal to 9.46 volt. So in this way, we got the no load voltage for the given circuit, that is equal to 9.46 volt. So similarly, let us find the value of the full load voltage. So here, when the radio is connected and it is drawing the full load current, that is the 100 milliampere current, at that time, the value of the Zener current will also change. So let's say at that time, the value of the Zener current is equal to Iz2. So this current Iz2 will be equal to Is minus IL, where the Is is this current, while the IL is equal to 100 milliampere. So we can say that this Iz2 is equal to Is minus 0.1 ampere. And here, this current Is is equal to 13.6 volt minus Vz divided by 18 ohm. So here, this Vz is equal to 9 volt plus 2 times Iz. So effectively we can say that this current Is is equal to 13.6 minus 9 plus 2 times Iz, or the Iz2 divided by 18 ohm. And of course, we will also have this 0.1 ampere. So we can say that this 18 times Iz2, that is equal to 13.6 minus 9 minus 2 times Iz2 minus 1.8 volt. Or we can say that this 20 times Iz2 is equal to 2.8 volt. That means here the value of the Iz2 is equal to 0.14 ampere. That means here this full load voltage is equal to 9 volt plus 2 times Iz2, and that is equal to 9 volt plus 2 times 0.14 ampere. That means the full load voltage is equal to 9.28 volt. So in this way, the value of the full load voltage is equal to 9.28 volt, while the no load voltage is equal to 9.46 volt. So from this we can say that the load regulation is equal to no load voltage minus full load voltage divided by full load voltage. So that is equal to 9.46 minus 9.28 divided by 9.28. And if we see the percentage wise, then that is equal to 1.93%. So in this way, for the given circuit, the value of the load regulation is equal to 1.93% when the supply voltage is equal to 13.6 volt. So similarly, let us find the line regulation. So we know that the percentage of line regulation can be given as this delta V out divided by delta V in times 100. So here the input voltage is changing between the 13.6 volt to the 11 volt. So for that, let us see the change in the output voltage. And here to find that change, here we will consider the no load condition. So whenever the supply voltage is equal to 11 volt, at that time let's say the output voltage is equal to VO1. So here this VO1 is equal to 9 volt plus 2 times IZ1. And here this IZ1 can be given as this 11 volt minus 9 volt divided by 2 ohm plus 18 ohm. That is this current. So we can say that here this VO1 is equal to 9 volt plus 2 times 2 divided by 20 ohm, and that is equal to 9.2 volt. So in this way we got the value of the VO1. So similarly, let us find the value of the VO2 when the supply voltage is equal to 13.6 volt. And earlier at the no load condition, we have already found the value of this VO2. So we have seen that this VO2 is equal to 9 volt plus 2 times IZ2, and that is equal to 9 volt plus 2 times this 13.6 minus 9 divided by 2 plus 18 ohm, and we have seen that that is equal to 9.46 volt. So in this way, when the supply voltage is changing from the 11 volt to the 13.6 volt, at that time the change in the output voltage is from 9.2 volt to the 9.46 volt. So we can say that here the line regulation is equal to 9.46 volt minus 9.2 volt divided by 13.6 volt minus 11 volt. So that is equal to 0.26 divided by 2.6 times 100, and that is equal to 10%. So we can say that for the given circuit, the line regulation is equal to 10%. So as you can see, due to the Zener resistance, when the supply voltage changes, then there is a significant change in the output voltage. So to minimize that, the value of the Zener resistance should be as small as possible. Alright, so now let us move to the next example. So in this question we have been given that the reference voltage for the constant voltage source is established using the voltage Vs, this resistor R1 as well as the Zener diode D1. So here we have been also given the value of the Zener resistance, and we have been also given that the zero current value of the Zener diode is equal to 5.6 volt. So basically here this Vz0 is equal to 5.6 volt. So this constant reference voltage is given to this op-amp circuit, and for this entire circuit we have been asked to find the value of the line regulation. And here we have been given that the given op-amp is the ideal op-amp. So considering this, let us find the value of the line regulation. So here, if we consider the Zener resistance and the value of the Vz0, then equivalently, this is how the circuit will look like. So for this circuit, let us find the line regulation. So here if you observe, then here we have not given the value of the source voltage. But here we will assume that the source voltage is changing by the plus minus delta Vs. So with the change in the source voltage, let us find the line regulation. So we know that in general, the line regulation or the source regulation can be given as the change in the output voltage due to the change in the input voltage. So here, first of all, let us find the output voltage. when the supply voltage is equal to Vs, and let's say that output voltage is equal to VO1. So here let's say the voltage across the Zener diode is equal to Vz, and the same voltage will appear over here. So we can say that here this V plus is equal to Vz. Now if you observe this op-amp circuit, then here the op-amp is configured in the non-inverting configuration. And we know that for the non-inverting configuration of the op-amp, its output voltage can be given as 1 plus this Rf divided by R1 times input voltage. So here for this op-amp, this feedback resistance is equal to 10 kilo ohm, and similarly this R1 is also equal to 10 kilo ohm, and here the input voltage is equal to Vz. So we can say that here this VO1 is equal to 2Vz. So here this voltage Vz is equal to this Vz naught plus Iz times Rz. So that is equal to 5.6 volt plus 10 ohm times Iz, and here this Iz is equal to Vs minus this 5.6 volt divided by 4.4 kilo ohm, that is 4400 plus 10 ohm, or we can say that is equal to 5.6 plus 10 divided by 4410 times Vs minus 5.6, or that is equal to 5.6 plus Vs minus 5.6 divided by 441. So if we see the output voltage Vout, then that is equal to 2 times Vz. That means simply this equation will get multiplied by the 2. That means we will have this 11.2 plus 2 divided by 441 times Vs minus 5.6. So that is the output voltage and the supply voltage is equal to Vs. Now whenever the supply voltage gets changed by the delta Vs, then in this equation the only thing that will change is this Vs. That means whenever the supply voltage becomes Vs plus delta Vs, at that time let's say the output becomes VO1 plus delta VO1, and that is equal to 11.2 plus 2 divided by 441 times this Vs plus delta Vs minus 5.6. So this is the value of the output voltage when the supply voltage changes by the delta Vs. So if we want to find the actual change in the output voltage or this delta VO1, then we need to subtract these two equations. And if we subtract these two equations, then the only term that will remain is this delta Vs. So we can say that this delta VO1 is equal to 2 divided by 441 times delta Vs. That means due to the change in the supply voltage, the change in the output voltage can be given by this expression. Or we can say that this delta VO1 divided by delta Vs is equal to 2 divided by 441. And for the percentage, we will multiply by the 100. So if we calculate the value, then it will come out as 0.453%. So we can say that for the given circuit, the value of the line regulation is equal to 0.453%. So similarly, now let us see the last example. So in this example also, we have been given the voltage regulator, but here the Zener diode is the ideal diode. But in this circuit, the op-amp is not ideal, and here we have been given that the open loop voltage gain of the op-amp is equal to 1000. So in the question we have been given that the no load current for the given circuit is equal to 1 milliampere, while the full load current is equal to 100 milliampere. So here for the given circuit, we have been asked to find the load regulation. So let us find that. So here, since the Zener diode is ideal, so the voltage at this node is same as the 6.3 volt. That means here this V plus is equal to 6.3 volt. And here let's say the voltage at this node is equal to V1. And similarly, let's say the voltage over here is equal to VO dash. So considering all these things, now let us find the load regulation. So we know that the load regulation can be given by this expression. That means here we need to find the no load voltage as well as the full load voltage. And then using this expression, we can find the percentage load regulation for the given circuit. So first of all, let us find the expression of the output voltage in terms of the load current. And for that, first of all, let us apply the KCL at this node. So applying the KCL at this V1 node, we can write this V1 divided by 10 kilo ohm, that is this current, plus V1 minus V0 divided by 10 kilo ohm, that is this current, is equal to 0. That means the summation of all the outgoing currents is equal to 0. So here this 10 kilo ohm will get cancelled out and we will have this 2V1 minus V0 is equal to 0. Or we can say that this Vout is equal to 2V1. So here we will use this expression later on. So similarly, now let us apply the KCL at this output node. So applying the KCL at output node, we can write this V0 divided by RL, that is this current, plus V0 minus V1 divided by 10 kilo ohm, that is this current, plus V0 minus V0 dash divided by 0.5 kilo ohm, that is this current, is equal to 0. So here this V0 divided by RL is nothing but the I0, that is the output current. And here this V0 dash is nothing but the open loop gain of the op-amp times V plus minus V minus. So that is equal to 1000 times this V plus, that is 6.3 volt minus V1. So further in this expression, let us put the value of the V1 as well as the Vout dash. So here this V1 is nothing but the V0 by 2. So we can write it as this I0 plus this V0 minus V0 divided by 2 divided by 10 kilo ohm plus V0 divided by 0.5 kilo ohm minus V0 dash divided by 0.5 kilo ohm, and that is equal to 0. So further we can write it as this V0 divided by 20 kilo ohm, that is this term, plus V0 divided by 0.5 kilo ohm minus 1000 times 6.3 minus V1 divided by 0.5 kilo ohm is equal to minus I0. So further if we simplify it, then we can write it as this V0 divided by 20 kilo ohm plus V0 divided by 0.5 kilo ohm minus 6300 divided by 0.5 kilo ohm plus 1000 times V1, that is 1000 times V0 divided by 2 times 0.5 kilo ohm, that is equal to minus I0. So further if we simplify it, then we can write it as this 0.05 times V0 plus 2 V0 plus 1000 times V0 minus 12,600 is equal to minus I0. And of course, here these entire terms will get multiplied by the 10 to the power minus 3 because in the denominator we have a 20 kilo ohm. So that is equal to 1002.05 times V0 times 10 to the power minus 3, that is equal to 12600 milliampere minus I0. So in this way, we got the relationship between the output voltage and the output current. So whenever the output current is equal to 1 milliampere, at that time, let's say this VO is equal to VO1. So that is equal to 12600 milliampere minus 1 milliampere divided by this 1002.05, and of course it will get multiplied by the 10 to the power minus 3, and that is the value of the VO1. So if you calculate, then that will come out as 12.573 volt. And similarly, when the output current or the load current is equal to 100 milliampere, at that time, let's say the output is equal to V02. So that will be equal to 12600 milliampere minus 100 milliampere divided by these 1002.05, and of course we will also have this 10 to the power minus 3, so that will be equal to 12.47 volt. So in this way we got the change in the output voltage when the load current is changing from the 1 milliampere to the 100 milliampere, and we know that this load regulation can be given by this expression. So here this voltage is the no load voltage while this voltage is the full load voltage. So we can say that the load regulation is equal to 12.573 volt minus 12.47 volt divided by 12.47 volt, and of course it will also get multiplied by the 100. So in the percentage, if we see the load regulation, then that is equal to 0.790%. So in this way, for the given circuit, we found the value of the load regulation, that is equal to 0.790%. So in this way, we can solve the examples on the line regulation and the load regulation based on the Zener Diode based voltage regulators. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.